At this very moment, trillions of stars burn brightly across the universe, each one powered by a process so efficient it could redefine the future of energy and humanity's place in the cosmos. Fusion, the same force that lights up these stars, holds the key to unlocking interstellar travel, a dream that has captivated us for centuries. But here's the astonishing part. Just 1 gram of fusion fuel can produce as much energy as 8 tons of oil. This isn't just about energy, it's about rewriting the rules of what's possible. Today, we're diving into how fusion energy could propel us to distant stars, overcoming challenges that once seemed insurmountable. From the science of harnessing stars on Earth to designing ships that can carry us to new worlds, this is the story of how fusion might just make humanity an interstellar species. Picture a tiny piece of the sun, harnessed here on Earth. This is the essence of fusion energy. At its core, fusion is the process of combining light atomic nuclei, like hydrogen, to form heavier elements, releasing a staggering amount of energy in the process. It's the same mechanism that powers stars, including our sun, but scaled down for human use. Unlike traditional nuclear fission, which splits heavy atoms apart and generates radioactive waste, fusion brings atoms together in a clean, efficient reaction. Think of it as a cosmic dance, where particles collide and merge, creating energy without the long-term environmental hazards. One of the most compelling advantages of fusion is its inherent safety. Because the reaction requires extreme conditions to sustain itself, any disruption causes it to stop almost instantly, eliminating the risk of runaway reactions. Additionally, the fuel for fusion, isotopes of hydrogen like deuterium and tritium, is abundant. Deuterium can be extracted from seawater, while tritium can be bred from lithium, meaning the fuel supply is virtually limitless. This makes fusion not only a cleaner option, but also a more sustainable one in the long term. However, the challenges are just as immense as the potential. To achieve fusion, we need to recreate the conditions found at the heart of a star, temperatures exceeding 100 million degrees Celsius and pressures that are almost unimaginable. Containing such extreme conditions is no small feat, requiring advanced technologies like magnetic confinement or laser-driven inertial confinement. Even then, sustaining these conditions long enough to produce net energy remains a significant hurdle. But these challenges are what make fusion such an exciting frontier in science and engineering. As we continue to push the boundaries of what's possible, the principles of fusion open up incredible opportunities, not just for energy production on Earth, but for powering the next generation of spacecraft. Imagine a future where interstellar ships are fueled by the same process that lights the stars, enabling us to explore the cosmos like never before. This is where the science of fusion meets the ambition of space travel. Picture this, a spacecraft hurtling through the void of space, its journey spanning thousands of years just to reach the nearest star. Sounds like something out of science fiction, right? Yet, this is the harsh reality of our current propulsion systems. Chemical rockets, the backbone of space exploration since the Apollo era, are simply not cut out for interstellar travel. They're slow, inefficient, and require enormous amounts of fuel just to escape Earth's gravity. Even with advancements in efficiency, chemical propulsion would take to reach even the closest star systems, far beyond the of any human crew or mission. This is where fusion energy enters the stage as a game changer. Unlike chemical rockets, which rely on burning fuel, fusion harnesses the same process that powers stars, combining atomic nuclei to release vast amounts of energy. The energy density of fusion is staggering. Just a small amount of fuel can produce millions of times more energy than traditional chemical reactions. This makes fusion not only powerful, but also sustainable, capable of providing the continuous thrust needed for long-duration space travel. Take the Daedalus Project, for example, a bold concept proposed in the 1970s that envisioned a fusion-powered spacecraft. Designed to travel to Barnard's star, approximately 6 light-years away, Daedalus relied on inertial confinement fusion to propel the craft at up to 12% the speed of light. While the project was purely hypothetical, it demonstrated the potential of fusion to reduce interstellar travel times to mere decades. Imagine cutting a journey that would take 30,000 years with current technology down to just 50 years. That's the transformative power of fusion. But what makes fusion so uniquely suited for interstellar travel? It's not just about raw energy output. Fusion engines could theoretically operate for years, even decades, providing a steady acceleration that builds up to incredible speeds over time. This sustained thrust is crucial for reaching the velocities needed to cross the vast distances between stars. Additionally, fusion produces minimal waste compared to other energy sources, making it a cleaner and more efficient option for long-term missions. Of course, the road to fusion-powered starships isn't without its challenges. The technology required to sustain a controlled fusion reaction in space is still in its infancy, and will need breakthroughs in fields like magnetic confinement, fuel containment, and energy conversion. Yet, the potential rewards are immense, opening the door to humanity's first steps beyond our solar system and into the broader galaxy. So, what are the specific technologies that could turn this vision into reality? Let's explore the innovations that are bringing us closer to fusion-powered interstellar travel. Consider the immense power of a star, harnessed and directed to propel us across the cosmos. That's the promise of fusion propulsion, a revolutionary system that could transform interstellar travel. Unlike traditional rockets, which rely on chemical combustion, fusion propulsion taps into the energy released when atomic nuclei fuse together, the same process that powers our sun. By converting this energy into thrust, we could achieve speeds that dwarf anything possible with today's technology. At its core, fusion propulsion relies on two main methods: magnetic confinement and inertial confinement. Magnetic confinement uses powerful magnetic fields to contain and stabilize superheated plasma, while inertial confinement compresses fuel pellets with intense laser beams to trigger fusion reactions. Both approaches aim to create the extreme conditions necessary for fusion, generating enormous amounts of energy in the process. This energy could then be channeled to produce continuous acceleration, allowing a spacecraft to build speed steadily over time without the need for massive fuel reserves. Imagine a rocket powered not by explosive bursts of chemical fuel, but by a controlled, star-like reaction at its core. This cosmic engine could theoretically propel a ship to a significant fraction of the speed of light, shrinking the vast distances between stars to decades. But harnessing this power isn't without its challenges. Managing the intense heat and radiation produced by fusion reactions in the unforgiving vacuum of space is a formidable obstacle. Engineers must design advanced shielding and cooling systems to protect both the spacecraft and its crew. The potential of fusion propulsion lies not just in its speed, but in its efficiency. By using small amounts of fuel to generate immense energy, it could make interstellar missions feasible without requiring impractical amounts of resources. So, how could such a system be integrated into a spacecraft? What would it take to build a vessel capable of harnessing the power of a star? Let's explore the next piece of this puzzle. Building a spacecraft around a fusion engine is no small feat. It's an architectural challenge on an interstellar scale. At the heart of the design lies the fusion engine itself, a powerhouse capable of generating immense energy but also posing unique risks. One of the first hurdles is radiation. Fusion reactions produce significant levels of radiation, which means the ship must be equipped with massive shielding to protect the crew. Think of it as wrapping the spacecraft in a high-tech cocoon, one that's thick enough to block harmful particles but still lightweight enough to avoid dragging the ship down. It's a delicate balancing act, where every layer of protection adds complexity to the overall design. Then there's the containment issue. Fusion engines require extreme conditions to function, temperatures hotter than the sun and pressures that are almost unimaginable. Containing that energy safely is a monumental engineering challenge. The materials used must withstand these conditions without failing, all while keeping the engine stable and efficient. It's like trying to bottle a star, and it pushes the boundaries of what we currently know about material science and engineering. Modularity becomes another critical factor. On missions that could span decades or even centuries, the ability to repair and upgrade the ship is essential. Imagine designing a spacecraft where key components can be swapped out or improved mid-journey, much like how the International Space Station has been upgraded over time. This modular approach ensures the ship remains functional and adaptable, even as technology evolves far from Earth. But scaling this up for an interstellar vessel adds layers of complexity, requiring systems that can operate autonomously and withstand the harsh conditions of deep space. Current spacecraft, like the International Space Station, give us a glimpse of what's possible, but the leap to an interstellar ship is staggering. The ISS is a marvel of engineering, but it orbits just a few hundred kilometers above Earth. An interstellar ship must endure the vacuum of space, cosmic radiation, and the physical strain of traveling at incredible speeds, all while carrying the hopes of humanity's future. Balancing power, safety, and efficiency is the ultimate goal. Every design decision must consider how these elements interact. Too much shielding adds weight, reducing efficiency. Too little compromises safety. The fusion engine must be powerful enough to propel the ship across unimaginable distances, yet stable enough to operate reliably for years. It's a puzzle that requires innovation, creativity, and a deep understanding of both physics and human needs. As we push forward with these designs, we're not just building a ship, we're crafting a vessel that could carry us to the stars. When it comes to powering interstellar ships, the choice of fuel isn't just a technical decision, it's a cosmic dilemma. Fusion energy offers two primary contenders, deuterium and helium-3. Deuterium, a heavy isotope of hydrogen, is abundant on Earth and relatively easy to extract from seawater. Its fusion reactions release massive amounts of energy, but they also produce significant amounts of neutrons, which can be problematic. Neutrons create radiation that damages spacecraft components over time, adding complexity and cost to interstellar missions. On the other hand, helium-3, a rare isotope of helium, is the golden child of fusion fuels. Its reactions are clean, producing minimal radiation and making it far safer and more efficient for long-duration space travel. The catch, helium-3 is virtually non-existent on Earth. So where do we find it? The answer lies in the stars, or rather, in places like the Moon and the atmospheres of gas giants like Jupiter. Mining helium-3 from these extraterrestrial sources is no small feat. It would require advanced robotics, space infrastructure, and a level of engineering we're only beginning to master. Imagine a cosmic gold rush, where nations and private companies race to secure this precious resource, not just for energy, but for the future of humanity's expansion into the stars. The economic and scientific potential is staggering, But so are the challenges. Securing helium-3 could redefine the economics of space exploration, turning distant moons and planets into valuable assets in our quest to reach the stars. Imagine a future where the cost of launching a spacecraft drops dramatically, not because of fuel savings alone, but because fusion energy has fundamentally reshaped the economics of space travel. Fusion power could change everything, making interstellar journeys not just possible but practical. The implications stretch far beyond the realm of science. They ripple through economies, industries, and even global politics. One of the most immediate impacts would be the democratization of space travel. Today, the high cost of fuel and energy limits access to a handful of governments and corporations. But fusion could level the playing field. With its near-limitless energy potential, fusion-powered ships would drastically reduce operational costs, opening the door for smaller enterprises, research organizations, and even private citizens to explore the cosmos. This shift could spark entirely new industries. Imagine interstellar trade routes, where resources mined from asteroids or distant planets are transported back to Earth, or space tourism that takes travelers beyond our solar system. The economic benefits don't stop there. Fusion technology could create millions of jobs, from engineers designing advanced spacecraft to technicians maintaining fusion reactors in orbit. Entire supply chains would emerge, supporting the construction and operation of these vessels. And as access to space becomes more affordable, we could see a boom in innovation, with startups developing technologies we can't yet imagine. But this future isn't without its challenges. As fusion becomes the cornerstone of space travel, nations will inevitably compete for access to the fuels and technologies that power it. Helium-3, a key component of many fusion reactions, is scarce on Earth but abundant on the Moon. Could this spark a new kind of space race, with countries vying for lunar resources? The geopolitical implications are immense, raising questions about who controls the energy of the future and how it's used. And then there's the ethical dimension. As we venture deeper into space, we'll face decisions about how we treat other worlds. Should we colonize distant planets or preserve them as untouched sanctuaries? What rights do future space settlers have, and how do we ensure fairness in this new frontier? These aren't just philosophical questions, they're practical ones that could shape the future of humanity. This technological leap won't just change how we travel, it will redefine how we live. As fusion energy propels us into the stars, it could also transform our societies, sparking new ideas, industries, and even ways of thinking about our place in the universe. As we look toward the stars and dream of interstellar travel, one of the most fascinating questions arises. How do we manage the immense power of fusion engines across the vast emptiness of space? Enter artificial intelligence. AI isn't just a buzzword here. It's the backbone of what could make fusion-powered ships not only possible but also reliable. Picture this, a fusion engine humming with energy, producing the kind of power that could propel us to distant galaxies. But such a complex system can't run on autopilot. It needs constant monitoring, precise adjustments, and the ability to respond to emergencies in real time. That's where AI steps in. Think about it, fusion reactions are delicate. Even the smallest imbalance could lead to catastrophic failure. AI would be tasked with keeping the reaction stable, optimizing energy output, and ensuring that every watt of power is distributed efficiently across the ship. But it doesn't stop there. In the unpredictable environment of deep space, where help is light years away, AI would also need to handle emergencies on its own. From sudden thrust fluctuations to potential reactor shutdowns, the system would have to make split-second decisions, often with no human intervention possible. We already see glimpses of this capability in today's space missions. Take autonomous rovers like NASA's Perseverance, which navigates the Martian terrain, avoids obstacles, and even conducts experiments with minimal human input. These systems are a testament to what AI can achieve in remote, high-stakes environments. But managing a fusion engine is a whole new level of complexity. It's not just about navigation or data collection. It's about controlling a process that could mean the difference between life and death for the crew. This brings us to one of the biggest challenges: creating AI systems that can make those life and death decisions. How do we program a machine to weigh risks, prioritize safety, and act decisively in situations where every second counts? It's a question that pushes the boundaries of both technology and ethics. And while the answers aren't simple, the stakes are too high to ignore. After all, the safety of fusion-powered travel doesn't just depend on the engine itself. It hinges on the intelligence that keeps it running. When it comes to fusion-powered spacecraft, the immense energy they harness also brings with it a set of unique safety challenges. One of the most pressing concerns is the risk of radiation leaks. Fusion reactions naturally produce high-energy particles, which, if not properly contained, could pose serious health risks to astronauts. But the challenges don't stop there. Reactor malfunctions, though rare, could lead to catastrophic outcomes in the harsh environment of space, where even a small error can have far-reaching consequences. To address these risks, engineers are developing cutting-edge solutions. Advanced shielding materials designed to absorb and deflect harmful radiation are at the forefront of these efforts. Think of it like the armor on a spaceship, but on a microscopic scale, layers of specialized alloys and composites working together to protect the crew. Additionally, fail-safe mechanisms are being integrated to automatically shut down the reactor in case of any irregularities. These systems are modeled after the safety protocols used in nuclear submarines, which have operated safely for decades in some of the most unforgiving environments on Earth. Redundancy is another key factor in ensuring crew survival. Imagine having multiple backup systems, each ready to take over if the primary one fails. This principle is crucial for interstellar travel, where help is light years away. Emergency systems, such as escape pods and self-sustaining life support, are also being designed to give astronauts the best chance of survival in the event of a crisis. These measures aren't just about preventing disaster. They're about creating a sense of security for those venturing into the unknown. The safety innovations developed for fusion-powered spacecraft don't just stop at the engines. They're shaping the way we think about interstellar habitats as well. From radiation-proof living quarters to modular design principles that allow for quick repairs, these advancements are laying the groundwork for a future where humans can thrive in deep space. It's a reminder that safety isn't just a feature, it's the foundation of every interstellar mission. As we look to the stars and dream of venturing beyond our solar system, one of the most critical hurdles we face is creating habitats that can sustain human life for years, even decades, in the void of deep space. Enter fusion energy, a power source so efficient it could be the key to building self-sustaining environments for long-duration interstellar missions. But what would such habitats look like? And how would they function in the harsh realities of space? Imagine a spacecraft not just as a vessel, but as a miniature Earth, complete with systems to grow food, recycle air and water, and maintain a stable environment for its crew. This is where fusion energy truly shines, offering the consistent, high-output power needed to keep these life support systems running smoothly. Current missions, like the Mars rovers, give us a glimpse of the challenges involved. These rovers rely on solar panels and batteries, which work well for shorter missions but fall short when it comes to the demands of interstellar travel. In deep space, sunlight is scarce, and traditional energy sources simply can't provide the relentless power required for tasks like growing crops or recycling waste. Fusion, with its ability to produce vast amounts of energy from a small amount of fuel, could revolutionize how we approach these challenges. Picture a habitat where hydroponic farms flourish under artificial light, powered by fusion reactors, or where advanced recycling systems turn waste back into usable resources with minimal energy loss. But it's not just about keeping people alive. It's about keeping them healthy and comfortable. One of the most intriguing possibilities is the creation of artificial gravity, a feature that could counteract the debilitating effects of prolonged weightlessness on the human body. By using fusion energy to power large, rotating habitats, we could simulate gravity, allowing astronauts to maintain their muscle mass and bone density over long missions. And then there's the psychological toll of isolation and confinement in deep space. Closed-loop ecosystems, powered by fusion, could not only provide physical sustainability, but also offer a sense of normalcy and connection to Earth, with green spaces and familiar routines helping to ease the mental strain. The road to creating these habitats is fraught with challenges, from developing reliable fusion reactors to designing systems that can function flawlessly for years without maintenance. Yet, the potential rewards are immense. Fusion energy could transform interstellar travel from a distant dream into a tangible reality, enabling us to explore the cosmos while ensuring the safety and well-being of those who journey into the unknown. And as we push the boundaries of what's possible, we also open the door to innovations that could benefit life here on Earth, from advanced recycling technologies to sustainable food production systems. The stars may be far away, but with fusion energy, they're closer than ever before. When we think about interstellar travel, the technical challenges often take center stage. The propulsion systems, the energy requirements, the vast distances. But there's another layer to this journey that's just as critical: the psychological and social well-being of the crew. Picture leaving Earth behind, knowing you might never return and that the journey itself could span decades or even centuries. The isolation, the monotony, the sheer weight of time could take a toll on even the most resilient individuals. Take, for example, life in Antarctic research stations or aboard long-term submarine missions. These environments, though earthbound, offer a glimpse into the psychological strain of prolonged isolation. Crews in these settings rely on strong interpersonal bonds, structured routines, and mental health support to stay grounded. On an interstellar ship, these factors would be even more vital. Cohesion among the crew wouldn't just be nice to have, it would be a matter of survival. To combat the mental strain, advanced technologies could play a pivotal role. Virtual reality systems might offer an escape, allowing crew members to visit Earth-like environments, engage in simulated social interactions, or even explore alien worlds from the safety of their ship. Hibernation technologies could also be a game changer, effectively reducing the subjective experience of time for those. But even with these tools, a robust framework for mental health care would be essential, ensuring that every member of the crew has access to counseling, therapy, and recreational activities to maintain morale. Interestingly, interstellar journeys might also reshape cultural and societal norms. Over time, the crew could develop their own unique traditions, languages, and ways of life, adapting to the challenges of their environment. This evolution could lead to a fascinating blend of earthbound heritage and spaceborne innovation, creating a truly new kind of human society. As we continue to explore the possibilities of interstellar travel, it's clear that the human element is just as important as the technological one. After all, even the most advanced ship is only as strong as the people who call it home. Imagine a future where humanity isn't just visiting the stars, but truly living among them. Fusion-powered interstellar ships wouldn't just carry us to new worlds. They'd carry our culture, our stories, and our very sense of identity into the cosmos. The journey itself could become a canvas for creativity, inspiring entirely new forms of art, literature, and philosophy. Picture novels written in zero gravity, paintings capturing the surreal beauty of distant nebulae, or music composed to echo the rhythms of deep space. But it's not just about creation, it's about evolution. As we travel further and for longer, our understanding of what it means to be human could fundamentally shift. What happens to traditions and values when generations are born and raised on interstellar ships, far from Earth's familiar shores? How do we preserve the essence of who we are while adapting to the challenges of life in deep space? These aren't just hypothetical questions. They're the cultural dilemmas we'll face as we venture beyond our solar system. And then there's the possibility of encountering extraterrestrial life, a moment that could redefine not just our culture, but our place in the universe. What might we learn from civilizations that have evolved under entirely different stars? The cultural impact of fusion-powered space travel isn't just about surviving the journey. It's about thriving, evolving, and discovering what it truly means to be human in an interstellar age. The search for extraterrestrial life has always captivated us, and with fusion-powered ships, that search could become a tangible reality. Imagine being able to travel to distant exoplanets, moons, and asteroid belts, places we've only theorized about or seen through telescopes. Fusion energy offers the kind of sustained power needed to make these journeys possible, unlocking the potential to explore regions of the cosmos that might harbor life. One of the most exciting prospects is the ability to investigate exoplanets within the habitable zones of their stars, where conditions might be just right for liquid water and, by extension, biological activity. Take Mars, for example. While it's relatively close, the discoveries there, like evidence of ancient water, have fueled our imagination about what lies beyond. With fusion-powered ships, we could venture much farther to places like Europa or Enceladus, where subsurface oceans might hide microbial life. But exploration isn't just about getting there. It's about what we can do once we arrive. Advanced telescopes and life detection instruments will be essential tools in this quest. Think of telescopes that can analyze the atmospheres of distant planets for signs of oxygen or methane, gases that could hint at biological processes. Pair that with robotic probes capable of drilling into icy moons or collecting samples from asteroid belts, and the possibilities become endless. This isn't just about finding life. It's about redefining our place in the universe. Fusion energy could propel us into an era where humanity isn't confined to Earth, but becomes an interstellar species, exploring and understanding the cosmos on a scale we've only dreamed of. The search for extraterrestrial life is more than a scientific endeavor. It's a journey that could unite us in our shared curiosity and ambition to explore the unknown. As we look toward the stars and ponder the potential for interstellar travel, one question looms larger than the technical challenges. What are the ethical implications of colonizing other star systems? It's not just about whether we can, it's about whether we should. Humanity has a complex history with exploration and colonization here on Earth, and those lessons must shape how we approach the cosmos. What happens if we encounter extraterrestrial life? What responsibilities do we have to preserve ecosystems that may exist light years away? And how do we ensure that interstellar colonies are governed in a way that's fair, sustainable, and respectful of all life forms. The possibility of discovering indigenous extraterrestrial life raises profound moral questions. If we find microbial organisms or even complex life forms on a distant planet, do we have the right to claim that world as our own? This isn't just a hypothetical scenario, it's a challenge to our values as a species. Imagine stumbling upon a thriving alien ecosystem. Would we prioritize our survival and expansion, or would we act as stewards, protecting the integrity of that environment? These decisions could define humanity's legacy in the universe. But the ethical dilemmas don't end there. Even if a star system is uninhabited, the way we establish colonies will speak volumes about who we are. How do we create governance systems that are equitable and just, especially when light years of distance separate us from Earth? Interstellar colonies will need to balance autonomy with accountability, ensuring that power isn't concentrated in the hands of a few. And sustainability will be key. Resources are finite, even in the vastness of space. We'll need to think long-term, designing societies that can thrive without compromising the worlds they inhabit. All of this leads to a deeper question. What gives humanity the right to expand into the cosmos? Is it our curiosity, our ingenuity, or something more fundamental? As we venture into the unknown, we carry with us not just technology, but the weight of our choices. The vision of an interstellar civilization isn't just about exploration. It's about becoming better versions of ourselves, learning from our past, and building a future that honors the principles of fairness, respect, and responsibility. And in that vision, the stars become not just destinations, but mirrors reflecting the best of what we can be. Picture a future where humanity isn't confined to a single star system, but has spread its wings across the galaxy, establishing thriving colonies on distant planets orbiting far-off suns. This isn't just science fiction. It's a vision of what could be if we continue to push the boundaries of technology and human ingenuity. In this interstellar civilization, the exchange of ideas, cultures, and resources wouldn't just be limited by the boundaries of Earth. It would span light years, creating a tapestry of collaboration and innovation on a scale we can barely comprehend today. Imagine the possibilities. Scientists from sharing breakthroughs with researchers in the Alpha system, artists from serious inspiring creators in the Orion Nebula, and economies fueled by resources mined from asteroid belts in multiple star systems. This isn't just about survival, it's about flourishing, about creating a universe where humanity thrives in ways that are as diverse as the stars themselves. To make this vision a reality, we'd need technologies that seem almost magical by today's standards. Think of a celestial network, a web of communication and transportation that connects these colonies seamlessly across the void of space. Advanced propulsion systems, like fusion-powered starships, would make interstellar travel not just possible, but efficient. Quantum communication could allow near-instantaneous exchange of information across vast distances, bridging the gap between worlds. And energy sources like fusion reactors would power these colonies, ensuring sustainability even in the harshest environments. This vision of a cosmic empire isn't about dominance, it's about unity. It's about humanity coming together across the stars to achieve something greater than any one civilization could accomplish alone. But to get there, we'll need more than just technological breakthroughs. We'll need a spirit of collaboration, a willingness to work across cultures, disciplines, and even species if we encounter them. It's a reminder that the future isn't just about what we build, it's about how we build it together. And with that kind of innovation and cooperation, the stars themselves could become our next frontier, Imagine trying to build the most complex machine in human history, one that could revolutionize energy and propel us to the stars. Now, picture doing it alone. It's an impossible task. Fusion energy and interstellar ships aren't just technological challenges, they're global challenges. To make them a reality, we need something equally powerful: collaboration. Bringing together the minds, the most advanced resources, and the combined efforts of nations and industries is the only way to push the boundaries of what's possible. But collaboration isn't as simple as it sounds. Sharing knowledge and resources across borders comes with its own set of hurdles. Intellectual property concerns, political tensions, and logistical challenges can slow progress. Still, history shows us that when we come together, we achieve the extraordinary. Take the International Space Station, for example. It's a marvel of international cooperation, built by NASA, ESA, and others. This orbiting laboratory proves that when nations pool their expertise and resources, they can create something far greater than the sum of its parts. Now apply that same spirit of collaboration to fusion energy and interstellar travel. Organizations like NASA and ESA are already leading the charge, but they're not alone. Private companies are stepping up, bringing innovation and agility to the table. Think of SpaceX, Blue Origin, and emerging fusion startups, each contributing unique skills and perspectives. Together, they're tackling problems that no single entity could solve alone. Yet obstacles remain. Fusion technology is still in its infancy, and interstellar travel is a distant dream. To bridge the gap, we need to overcome challenges like funding shortages, technical limitations, and the sheer scale of the problems we're facing. But here's the thing: every challenge is an opportunity for collaboration. By working together, sharing risks and rewards, and staying focused on the bigger picture, we can turn these obstacles into stepping stones. So what's next? The path to fusion and the stars isn't just about building better engines or reactors. It's about building bridges. Bridges between nations, disciplines, and industries. It's about recognizing that the future of humanity isn't a solo mission. It's a team effort. And when that team comes together, there's no limit to what we can achieve. Fusion energy might hold the key to interstellar travel, but the path to achieving it is anything but straightforward. Think of it like climbing a cosmic mountain, an exhilarating yet daunting challenge. The first major hurdle is the sheer complexity of the technology. Fusion requires recreating the conditions at the heart of a star, where temperatures soar to millions of degrees and pressures are unimaginably high. Containing this plasma in a stable, controlled environment has proven to be one of the most difficult feats in modern science. And even when we manage to sustain a reaction, the energy output often struggles to surpass the immense energy input required to ignite it. Then there's the financial side of the equation. Fusion research isn't just expensive, it's astronomically costly. Projects like ITER, the International Fusion Reactor Experiment, have budgets stretching into the tens of billions of dollars. These kinds of investments require long-term commitment from governments and private sectors alike, and with so many competing priorities, securing consistent funding can feel like navigating a political minefield. Public support is another critical factor. While fusion energy promises clean, nearly limitless power, it's still seen by many as a distant dream rather than an immediate solution. Building awareness and enthusiasm for its potential is essential to driving the momentum needed to push past these barriers. But despite these obstacles, progress is being made. ITER is steadily advancing toward its goal of demonstrating a self-sustaining fusion reaction by the 2030s. Meanwhile, private companies like Energy are pioneering innovative approaches, such as compact fusion reactors, that could accelerate the timeline. These efforts, though challenging, are laying the groundwork for a future where fusion energy becomes a reality. And the rewards, they're nothing short of transformative. Overcoming these hurdles could unlock a new era of energy abundance, paving the way for technologies like interstellar ships that once seemed confined to the realm of science fiction. The climb may be steep, but the view from the summit promises to be worth every step. What if humanity could step beyond the confines of Earth and venture into the cosmos, not as explorers of a single planet, but as travelers of the stars? Fusion-powered interstellar travel isn't just a far-off dream, it's a potential gateway to a future brimming with possibilities. Imagine unlocking new scientific frontiers, from studying alien ecosystems to uncovering the origins of the universe itself. Each journey could lead to breakthroughs that redefine our understanding of physics, biology, and even the nature of existence. And it's not just about science. The cultural impact could be profound, as encounters with other worlds might reshape our art, philosophy, and sense of identity. But perhaps the most compelling reward is the chance to ensure humanity's survival. Earth is a fragile oasis in a vast and often hostile universe. Climate change, asteroids, or other global catastrophes could threaten our existence within a century. Fusion-powered ships could give us the means to escape these risks, dispersing humanity across the stars and securing our future. This isn't just about exploration, it's about preservation. What does it mean to be a species that no longer relies on a single planet? How would our perspective on life, resources, and responsibility evolve if we became an interstellar civilization? To achieve this, we'll need more than just technological innovation. It will require a collective commitment, a shared vision that spans generations. The journey to the stars won't happen overnight, but the rewards are worth the effort. So, as we look to the future, let's ask ourselves, what kind of legacy do we want to leave? Will we remain bound to Earth, or will we embrace the stars and the limitless potential they hold? The choice is ours, and the time to start is now. Picture this: humanity, no longer confined to the cradle of Earth, stepping into the vastness of space as an interstellar species. It's a vision that feels both audacious and inevitable, a cosmic journey that could redefine what it means to be human. But how do we get there? The path to the stars begins with a single spark: fusion energy. This isn't just about powering our homes or cities, it's about unlocking the potential to travel beyond our solar system. Fusion energy, with its virtually limitless supply of clean power, could be the key to building the kind of interstellar ships that once existed only in science fiction. Imagine vessels gliding through the void, sustained by the same processes that fuel the sun itself. But fusion is just the beginning. To reach the stars, we'll need more than breakthroughs in energy. We'll need a collective leap in innovation. Think about the challenges: designing ships that can withstand decades or even centuries in space, creating self-sustaining ecosystems, and protecting astronauts from the harsh realities of cosmic radiation. Each of these hurdles will require creativity, determination, and a willingness to think beyond the boundaries of what we know. It's not just about solving technical problems. It's about fostering a mindset that embraces the unknown and dares to dream big. Education will play a pivotal role in this journey. Inspiring the next generation of scientists, engineers, and visionaries is essential. We need classrooms that nurture curiosity, labs that encourage experimentation, and societies that value the pursuit of knowledge. And let's not forget the power of global cooperation. This isn't a challenge for one nation or one group. It's a shared endeavor that transcends borders and unites us in a common purpose. When we work together, combining our resources and expertise, we can achieve what once seemed impossible. This voyage to the stars isn't just about exploration, it's about survival. Earth is our home, but it's also a fragile one. Becoming an interstellar species ensures that humanity's story continues, no matter what challenges we face on our planet. It's a legacy that extends beyond our lifetime, a gift to future generations who will carry the torch of discovery. The road ahead is long, and the challenges are immense, but the rewards are beyond measure. By harnessing fusion energy, fostering innovation, and uniting as a global community, we can turn this vision into reality. The stars are calling, and humanity is ready to answer. As we bring this exploration to a close, it's clear that fusion energy isn't just a scientific breakthrough. It's the key to unlocking the stars. The potential to harness this nearly limitless power source could redefine what's possible, turning interstellar travel from science fiction into a tangible goal. But let's not forget the challenges we've discussed. The immense technical hurdles, the need for groundbreaking engineering, and the global collaboration required to make it happen. These aren't roadblocks, they're opportunities for innovation, for humanity to come together and push the boundaries of what we can achieve. Imagine a future where our descendants look back at this moment as the turning point, the spark that ignited our journey to the stars. As Carl Sagan once said, somewhere, something incredible is waiting to be known. That incredible something could be within our reach, thanks to the power of fusion energy. So what do you think? Will fusion be the driving force that propels us into the cosmos? Share your thoughts in the comments below. We'd love to hear your perspective. And if you're as excited about the future of technology as we are, don't forget to subscribe and join us as we continue to explore the frontiers of innovation. The stars aren't just a destination, they're a calling. Let's answer it together.